First you choose your 0, see what your options are, where can I place all the poles, and then play around with it. Then increase the gain, try to move them where all of them make sense. They're still well separated, right? So you will see these two poles. If you have two, you will again see them in their dynamic stiffness, right? So make sure they're far enough apart. Otherwise, you get resonant properties, right? So the same applies to this, but it's a little harder to place the eigenvalues. But in the end, it's the same thing. You can get the same behavior as continuous domain. But you have these three options. Let's do the easiest real quick, so we have one solution. Let's say we did mathematically the easiest one, to do the purple one, right? We cancel it, and then the closed loop basically becomes k over b times 1 minus e to the minus t over 12 over Right, so these are gone, and then kb, that's our gain, and this, and then we can again multiply this down there to make it look a little nicer. Plus kb, oh, k over b. Right? And now to really see the pole, I just multiply times z. There's each minus 1 is missing. Oh yeah. Just up here and here. Sorry, I missed the z to the minus 1. So basically this is gone, this is gone. This changed a little bit. So for the full 0, should look like this. Hopefully I didn't do the algebra wrong. I literally just did this. Hopefully this is okay, but try it yourself. You have to do it in your homework anyways. But this is now your pole, right? So now I have an equation for your pole, which is e to the minus pole t, right? So now you can place this. You can basically tell this what it is. You can say this should be 2 pi 300, for instance, in your homework, right? You choose this eigenvalue to be 300 hertz fast, put it in here, that makes that, then you know that this should be equal this. So from that you get your k. With your k and your dc you already chose, right? Your dc was e to the minus t over tau. The cancellation, right? Was already set here. Your dc is this. So from dc and ka you get kp, from that you get your ki, and you're done. Right? So that's one way to do this. There's two others that I showed you with other zero point placement. And they will have other properties because the eigenvalues are different. Right? Okay. So we'll hand out the homework now. Homework 3. and have a look at it and maybe your questions. It is a little shorter than the other ones, but also the concepts are a little bit newer, I think. So that's okay. Any questions regarding the homework? Also homework 2 or homework 1 if you want to. So I really don't want to show you the answers just yet. But this, for instance, now the easy version of how you're supposed to model this, okay? Here's like an input, that would be the voltage, 0 order volt, that's how the block looks like in MATLAB. And then we have our RL, right? then resample and look at the sample. You can also have a look at the continuous, both at the same time. These will be your reference. That is the real system. That's how all of your approximations, or your actual model, should yield the exact same results as this. Otherwise, something is wrong with the math. Then you have, for instance, Tustin. Right? I now just did a Tustin of this. Exactly where you want to rest this, I put this Tustin equation, one rel, and everything else I leave. And hope for the best. And then I can use the rectangular format, same thing, I put it here, rest I leave. The bottom one I won't show you because that's what you were supposed to do. But it looks pretty similar to what we did today. And you should see that they don't wind up with the same solution. And now it's command out. No, it's not. I won't show you the control just yet. But we did it on the table. Okay. And then you should see something like this. Where the yellow is your continuous signal, and one of them samples exactly the same thing. Some of them look a little bit different. I don't want to show, now you have it on video anyways. But this is sort of what you should see. The correct discrete model should yield the exact same result, whereas other approximations won't do the same thing. They will look very, very different, and totally depending on the tau and all the other things involved in your differential equation, it can change.
The green one is the actual decrease?
The green one is the one that we just did together. Right? It's at all the sampling points, it looks exactly. I actually also have the sampled continuous one that's purple, but it's exact on top of the green, so you can't see it. So, just to make sure that you can trust me, I now take off the correct one, and now we should see the purple line. Before we couldn't. You see this? Oh, the purple line is here. So the green one was overlapping exactly with the purple one. And all the others don't. There's a reason why we do this. Okay? Correct discrete modeling really enhances your models at all, and it enables you to put the eigenvalues also exactly where they are. And if you leave some things out, or you have a bad approximation, your eigenvalues might be everywhere. No idea, and you're just trying out and hope for the best. Okay? So this is sort of what you should see in your homework. I'll just try to throw you a bone here that you see why we're doing this, okay? It's not just for something or for nothing, it's really important. It can make a huge difference. You should see this in the homework. Okay, I think time's up. Thank you. So, yeah, if you don't have any further questions, yeah, see you next time. You can always email me, come to my office, we can talk about the homework problem. So we have one more lesson, and it's hard to really put everything in that I would like to teach you. So you can also choose, like all of the continuous stuff that we did. Maybe you have a think about when you now do this discrete stuff. Maybe you have something you really want to see.
Can we do something very practical when we can see directly with the discrete control?
Do you want to do what? Say that again.
Discrete control, but we want to see when we implement with this one, or when we change different scheme, and then what is the result, and then compare with the continuous one and what is different.
With the approximation. I mean, this is homework 3 right now, right? We will basically see the difference between continuous or the just an approximation But you can try here also, right? You already built these models. You can use now the same KP and KI from your continuous. That won't work at all. Obviously, these are totally off. They have to be dependent on the TS, right? If they're not depending on sampling, that cannot be right. So that you have to choose a very, very fast sampling time. That I don't even know if that works. But the different approximation models, we see in here the difference. We can also have a look at these models that I have here prepared together if you want to, and see where it makes a lot, where's the biggest difference. But I was more thinking about, so observers I would like to show you in discrete time, for instance, a Loomenburger cell observer for the system, because that's really helpful for many different reasons, right? Observers are always great, but also I will also want to talk about computational delay, because now we don't have computational delay here, right? We have a latch, and that's it. But in real life, we sample, and we have to do math, right? Math takes time. We sample the current, and we try to update the voltage at the same time, or the force. We can't. We have to do first our current control math, and that means we have a delay. So we have to deal with that as well. We have to include this in our differential equations. That I would like to teach you. I would like to teach you observers, and also how observers can help you with the time delay. A couple of these things. Maybe feed forward as well, but we can't really put everything in there. But the concepts, now that you understood them in continuous domain, I think you can come up with how you do it in discrete. Like feed forward, very simple, right? It's the inverse of the plant. It doesn't matter if it's an S or a 1 over S. You know the plant, you do 1 over. That's your feed forward. Then there's deadbeat control that basically works a little bit like an inverse. I don't know if you know what deadbeat is. It also means you reached your command within one sampling period.
Deadbeat control.
Yeah. You can also build deadbeat observers. They always work because your parameters are exactly the one that you put there. Yes, so there's many different things and many different concepts that we can have a look at, or maybe you want to look at a certain plant.
State space control.
I mean, this is all space-based.
State space is a little bit different with this one on conventional and base.
Yeah, we won't go into the state space format, no. Because state space format is really not that beneficial. I think the physics-based control I would always leave it in that format.
For the grid, if we don't want to do conventional, don't want to depend on the high frequency sampling, and then normally they choose with the state space model.
So state space model just means that you have a different formatting of your block diagram, right? Right
yes.
now we use the manipulator input as we have everything in the units of the manipulator input. Mm-hmm. We could also change it around as the unit of the state, or of the derivative of the state. However, that is really not all that helpful for designing a control.
Yeah, I think they can find the information.
Yeah. So I would not recommend doing. We can certainly play around with it. The observers look pretty similar. It's literally just a gain that you shift over. So yes, we can do that too. It's pretty much the same. But I usually wouldn't like to go there.
Yeah, it depends.
Yeah.
Or just go with some basic and then see.
Okay, but if you have any recommendations or anything you want to have a look at, email me or let me know, and I try to put it also into the last course, in the last lesson. Also depends a little bit on the time, and also don't do it the day before because it also takes time to prepare. Okay, cool. Hope this was helpful. By the way, here, this is also in your handout, right? Just to explain, so phase experience, we didn't just want to know what the break frequency is. And we have this other one. And we had this. So this was basically showing you how to do the Tuscan approximation, and this is what we did, right? Before in continuous, we only went from time to transfer function and back, right? We could play like this. What we did now is we solved it in the 10 steps. So we went to transfer function, with the initial conditions, went back to impulse, did the sampling, and so we did basically this kind of steps. Whereas the cookbook method would do this step, and for the transfer function, use the cookbook method to get here. This was just a little bit that you know where we're moving around. And this here tells you what the eigenvalues in Z-domain are doing. Basically also the same thing we did before. These are the time step responses, or the impulse responses, if you have these kind of conjugate poles. And on the left-hand side, these planes, when they happen to be on the left side, like these or these and these, you see that at every sampling time, they change direction. So they have a frequency that's exactly your sampling frequency. You see this? It's always going up and down, up and down, up and down. But they're not unstable. So it looks a little bit weird. And the frequency of this has nothing to do with the poles are. The frequency is always your sampling frequency. And this is what we call forced oscillation. So the left-hand side, they are stable and they can be better damped, like here it's really well damped, or worse damped. But you always will see this in your manipulated input. You don't see this actually in your state. This is like when you try to drive 50 kilometers an hour and you push the pedal all the way in and then you leave it. And you push it all the way in, and then you leave it. And that's the way you try to hold this 50. It's almost like a two-point controller. And maybe at every sample instance, the speed is going up and down and up and down, and you actually hit it exactly in the middle, and it looks like you're not changing your speed, but in the car you feel it. When it continues, you feel it. But in the sample point, you might not even feel it. That's forced oscillation. In real world, you feel this, but if you sample it, it seems like the speed is actually continuous. Or it's actually not jumping, but that's forced oscillation. It's not good. We don't want to be on the left-hand side. They are stable, and they can be damped, and if they have to be there, then really dampen them well, but that's what you see. If you place a pole lever there, you will see this in your, especially in your manipulated input. It will always jump back and forth with the sampling frequency. That's why we don't want them there. Okay.
You need help?
Should be fine.